If I were to draw a circle on this piece of paper, I would place my hand on the page and then draw a circle using my fingers while my hand provided a stable reference. However, if I took my hand out of that equation and tried to only touch the page with my pen, my circle gets a little uglier. I don't have that stable reference. I'm only touching the page with my pen, and there's not a solid connection. Well, that's exactly what happens in a skidless, or kind of the laboratory-style roughness gauge. We have the stylus that touches the surface we're measuring, and there's not a real solid connection between the two. Now, this measuring system is going to have, obviously, a surface that's most likely sitting on a table or a bench or something, and that is connected to the stylus, but through a rather long path. There's a table with perhaps a column and a drive unit back here, and this drive unit is going to house the probe that travels along through an internal reference. Now, the probe, the electronics, are connected to the stylus with a pivot perhaps along the way, and this measuring loop is rather large. If I go from the surface all the way back around through the system to the stylus itself, we have a rather large loop. Now, a large measuring loop means that we're susceptible to things like vibration. If something shakes this, there are lots of flexible pieces along the way at a microscopic scale, which is going to allow the vibration into our measurement. So let's take that analogy of placing my hand on the page along with my pen and see how we can tighten up this measuring loop. Let's go back to the same setup of a stylus touching the surface, but this time let's put the stylus pivot inside a skid. So the stylus is going to touch the surface, but also touching the surface, let's use my hand, not just the pen. And that plays out in roughness as using a skid, which is a large radius sitting on the surface that pivots and follows the trends of the surface on its own kind of motion. So the skid is going to pivot back here, keeping the whole system in range while the stylus pivots inside. And this skidded approach is common in many of our portable gauges. The stylus pivots inside a larger skid that keeps it in range. This stylus is always going to stay generally inside its measuring range as the skid pivots and follows the trends, or more importantly, the skid may pivot and follow any vibration as the surface moves. The surface moving up and down is going to move the skid up and down, which is kind of canceled out and makes a stable shop floor kind of measurement. Now, this works great in the shop floor setting, but what if we have perhaps some waviness on the surface? Here's a surface with a hump in it. Well, that surface is going to be followed by the skid and the stylus. The skid is going to kind of tilt down and follow things here, and then the skid will tilt up at the top and follow kind of here, and then at the other side again the skid will more or less tilt down as it gets to this side. The skid will follow the trend of the surface, and as a result, the stylus won't see that waviness. The stylus will simply see the roughness as the skid cancels the waviness away. So this hump inside the surface is going to be canceled out by the skid motion. Now, that may be okay. Maybe we only care about roughness in our setting, and this is going to give us a reliable roughness measurement because the vibration, our biggest uncertainty contributor, is canceled out. However, there's one more catch. Not only does the skidded roughness system hide waviness, it can also have problems when there's dirt on the surface. Let's imagine a case where we have a fine surface with a spike of dirt on it. In this case, there's going to be some point along the way where the skid itself rides up on the dirt. And when the skid is riding up on the dirt, the stylus inside has to pivot downward to stay in contact. So the skid rides up about its pivot, and the stylus is going to have to reach down relative to its own pivot. When the stylus reaches down, the measurement becomes a valley. So a skidded gauge is going to introduce an artificial valley when there's a peak in our surface. Now this original surface doesn't have anything but a peak and flat regions, but the measured result has a flat region and a peak, and then a dip where the stylus had to reach farther down while the skid was up in the air. This is happening all the time, and in many cases we will get data that just simply looks like this with a dip in it because the skid encountered the dirt and the stylus missed it because the stylus may not be on the same path, or the stylus is a narrow path compared to the skid's path. So a skidded measurement system is a fantastic way to look at roughness on the shop floor. It will cancel out our biggest uncertainty contributor due to a measuring loop that's now very, very small, but the expense is we lose the ability to see waviness, and we can introduce errors when there's something like dirt on the surface. So be careful. A skidded gauge may solve many of your shop floor challenges, but it comes with some costs. To find out more about skidded measurement, or to improve your measurement systems, or even understand them better, reach out to us at digitalmetrology.com. We're glad to help.